Hello everyone, my name is Dr. Andrew Pierce, and today I'll be narrating a slideshow for you that I hope will help you understand fire behavior in some of the fuels that we have here in Hawaii. The title of my talk is Comparing Fuel Models for Fire Behavior Prediction with Observed Fire during a prescribed fire at Hawaii Volcanoes National Park. I'd like to thank my partners in this endeavor. Sierra McDaniel and Mark Wasser from the Park Service helped me out a lot. They're the ones who invited me to the park to do the study. And my supervisors and supporters, Creighton Litton, Susan Cordell, and Christian Giardina. I'd also like to thank Doug Cram of the Pacific Fire Exchange for encouraging me to record this. And also Elizabeth Pickett at the Pacific Fire Exchange for making the Pacific Fire Exchange an important part of the picture in fire management in Hawaii. So by way of introduction, I just wanted to talk a little bit about fuels beds in Hawaii before I get to the specifics of the study. Fuels in Hawaii are highly variable. I would say even more variable than the continental U.S., the mainland U.S., and that's because we have grasses here that are 2 to 3 feet in height, or excuse me, 2 to 3 meters in height. That's much taller than you get on the mainland. We have trees with non-traditional boles, palm trees, tree ferns, these types of plants. Their trunks don't grow the way that trunks grow on the mainland, and so that provides a different fuel component. And then you have invasive species of all kinds. Hawaii is notorious for the amount and number of invasive species that we have to deal with here. And so those are all over, and they provide an even more complex picture to the fuel bed. And because of this, some of the fuel complexes in Hawaii are not well represented by standard fuel models. So standard fuel models are the ones that were developed mostly for the mainland. But today, you'll see that some of my data suggests that some fuel complexes in Hawaii are represented well. So to keep the picture a little bit general for a couple more minutes, one of the important things about Hawaii is that there's an extremely steep gradient in rainfall. And so by that I mean on one side of the island you have less than 75 centimeters of annual rainfall in the Kauai area, and then less than 40 kilometers away on the Hamakua coast, you have over 6 meters of rainfall every year. The same is true of of temperature gradients. It's very hot and dry over here, hot and dry over here in the Kona side. It's also really hot down in Kalapana, in East Pahoa. But then it's cool up on tops of the mountains. So you have steep gradients of temperature and precipitation. And so that drives a lot of variation in hypothetical fire regimes. The graph I'm showing you here, along the bottom axis you have warm and dry on the left and wet and cold on the right. And so these are hypothetical climates, wet and cold and warm and dry. And then on the y-axis, you have the period between fires in years. Notice that this is not linear, it's logarithmic. And so the very longest fire intervals of 1,000 years are way here at the top. Then the next order down, 100 years across here. And this is where you start to see fire regimes that we understand. And then 10 years down here, that's very short. So this is where we have regimes of very, very frequent fires. Now, in Hawaii, we have most of these types of ecosystems. We certainly have hot, dry desert in Kauai, and over there, it's hot and dry, so it's definitely dry enough for fire, but the limiting factor is fuels. And so there's not as much fuel in Kauai to drive fires, and so it takes a long time for those fuels to build up. Getting towards Ka'u, South Ka'u, you started to get dry range, and this is also true the closer you get to Waimea from the Kona side. Dry range is characterized by moderate interval fires, and that's driven by fuel accumulation and weather conditions. And then the most frequent fires are in places where it's dry enough most years to have a fire, but it's also wet enough to grow plenty of vegetation in order to burn. And this is the kind of system that I'll be talking about today. And that system is the coastal lowlands of Hawaii Volcanoes National Park. Here's just a picture of the Pali down on Chain of Craters Road from Hawaii Volcanoes National Park. You can see lava flows and little kipuka of vegetation. You can see that the vegetation is not trees, it's shrubs and grasses. Just to give you an idea, this part of Hawaii Volcanoes National Park lies in one of the climate zones in Hawaii that we call tropical summer dry, which means it has a dry season, but it also has a wet season. And so that wet season provides enough moisture for the vegetation to grow and create a fuel bed that's flammable, but it also has a dry part to it, which means the vegetation dries out and those fuels dry out enough that you can carry fire across that landscape. So down on the Chain of Craters Road, which you can see right here, is a little kapuka. It's not that little, it's about 100 hectares, called Kealakamo Waina. This is the kapuka right here. It's kind of got two pieces, and then the lower part, which is all joined, so it's kind of got a split in the middle. This is where we did the prescribed fire. And before we did the fire, we wanted to know what kinds of vegetation were there. And so this part of Hawaii Volcanoes National Park is a coastal lowland. It tends to burn. It's dominated by invasive grasses. You can see the two most important invasive grasses are Malinus species. This is molasses grass, Malinus minutiflora, and Natal redtop, Malinus repens. On the native side, you have Wolftheria indica, which is the most important native species, and you have small amounts of Heteropogon contortus, which is the native peely grass. But overall, your native cover is much, much lower than your invasive cover. As far as biomass is concerned, again, you have Natal redtop, very much the most dominant species in terms of biomass. But in second place, you have peely grass. Peely grass is an important part of this system. You also have lots of litter that can burn, and so overall, you have quite a lot of fuel, over 8 metric tons per hectare. In the field, we set up transects to measure the fuels, to measure the vegetation, and so in conjunction with sampling for the live biomass and percent cover, we use these transects as bronze transects to sample fuels, and those fuels come in various size classes, and they look like this. So 1 hour fuels, this is the little stuff, less than 1/4 of an inch. On average, was just about a little more than 1/3 of a metric ton per hectare. The 10-hour fuels, this is 1/4 to 1 inch. They were more variable, and they averaged about 3 metric tons per hectare. 100-hour component, this is stuff that's 1 inch to 3 inches. There wasn't very much of that at all because the vegetation that we were in just does not get that big. We had a few scattered a'ali'i shrubs and some other shrubs, but not many of them even reached that size. By far the largest component, though, was the live herbaceous component. This is all the grasses that I was mentioning before, the peely grass, the molasses grass, the Natal redtop. And so some of our transects had over 18 metric tons per hectare, but some of them had very little. And so the average turned out to be something like a little less than 6. And finally, we had live woody components. So this is the live shrubs that we had. So there were live shrubs that just, didn't make it into the 100-hour class. So live shrubs were also an important part. In order to get an idea of what kind of fire behavior we were expecting, we measured the fuel loads, and like I said, this is the averages that we computed. So again, 1 hour fuels. This is less than a quarter inch. We had a half of a metric ton per hectare. The 10-hour fuels from a quarter to 1 inch, just over 3 metric tons per hectare. 100-hour fuels, very small load, just a tenth of a metric ton per hectare. But again, the most dominant part of the fuel bed is this live herbaceous load. So we had 5.7 metric tons per hectare of live grasses. We also had 2.5 tons of live shrubs. So in this fuel complex, the vast majority of our fuels are in the live category here. We also measured fuel bed depth, and that fuel bed depth is 67 centimeters. That's just a little bit more than 2 feet. So you can imagine walking through a field that's covered in 2-foot-high grasses. We also computed fuel moistures. This is an important part of predicting fire behavior, is knowing how moist the fuel is. Because if the fuel is too moist, it's not going to burn, and you don't want your model to say it's going to burn if it's too wet to burn. So we computed fuel moistures for these species and these size classes. You can see the range of computed moistures we had here. And then we calculated a cover-weighted mean of fuel moistures. And so our live woody fuel moisture was about 250%. Live herbaceous fuel moisture is very dry, 30%. And our 1 hour fuels, 8%, and our 10-hour fuels, 9%. So these fuels are really dry. I should mention also, we measured these fuel moistures 1 day before the fire started. So the fire was scheduled for 1 day, and then the day before we went out and we sampled these fuel moistures between noon and 1 p.m. So we got them pretty much when we expect them to be about the same as we'd expect them to be during the fire. We also wanted to compare our observed fuel moistures with what a RAWS weather station would predict. And RAWS weather stations are an important part of fire management because these are, RAWS stands for Remote Automated Weather Station. These are really important all across the mainland because they go out and they set up the RAWS stations. It sits out there for years and years and years and collects weather data and reports fuel moistures, and these are a very important part of the mainland modeling system, and we wanted to know how well they would work in Hawaii. And so here you can see a comparison of the fuel moistures that we observed here on the left with the fuel moistures that the RAWS station reported here on the right. And so there's some differences and some similarities. The herbaceous number is about the same. The live woody number is much smaller on the RAWS, and the dead stuff is higher on the RAWS. Here's a comparison of our custom fuel model that I just described with some standard fuel models. These are standard fuel models from, number 3 is from Albini, 1976. And these GR and GS models are from Scott and Bergen, 2005. So you can see our fuel model here, and then some of these fuel models have different parameters. And I'll talk about those differences again later. Just so you can get some excitement, this is what the fire looked like as it was burning. We had winds that were coming from the north-northeast and blowing to the south-southwest. So that's right to left across the screen. You can see some pretty impressive flame heights. These are flame heights that are getting up to almost 15 feet. So that's pretty hefty. Here's our intrepid fire personnel. She was the one who was out there actually lighting the fire. Here's another shot from a different angle. You can see the ocean very close in the background. It also gives you an idea of what sort of elevation we're at, which is just over about 150 feet. Another one here, our intrepid fire personnel lighting the fire away, and a shot of some combustion activity. You can also see the kapuka, the lava flow around the kapuka, which is what enabled us to get so close to record the progress of the fire. Okay, so what did we actually see from this fire? What we saw from the fire was that here on the very left column, you're going to see our custom fuel model. And then across the bottom you'll see the names of the other fuel models. And then this heavy dark line across is what we observed the fire behavior to be with our error estimates on either side. And so our custom fuel model with the observed fuels along with the observed weather over-predicted our rates of spread just a little bit. And when we switched over to the RAWS weather, which is the weather station weather, we over-predicted rate of spread a little bit more. I want to point out model GS3, which is a standard model. When we use the observed weather, we under-predicted a little bit, and when we use the RAWS weather, we over-predicted a little bit. Now let's look at flame length. So flame length was the other variable we were interested in. Again, custom model here on the left, standard fuel models stretching to the right, and the heavy line is the observed flame length. So our custom fuel model over-predicted flame length. Not too bad, but a significant amount. But again, I want to point out on the right side here, model GS3 did a pretty good job of predicting flame lengths. Now, the last thing that I want to talk a little bit about is comparisons among the fuel models. So what we did here was we computed a statistic that's somewhat akin to a root mean squared error. And what we did was we said, okay, if the custom model is true, if that's exactly what it is, how different are these other models? And so we calculated a statistic based on the differences between each of these standard fuel models and the custom fuel model to give each one a score. And I just want to point out that model GS standard, this is a standard model, GS3 was the closest. It had the smallest difference, was the least different from the custom fuel model. And you can see that here. So this is the closest one to the custom fuel model. This one was number 2, and this one was number 3. So you can see that as you get farther away in terms of fuel loads, you get farther away in terms of your predictive accuracy. The same is true when you compare flame length. So this was the closest model to the custom fuel model. This was next, and this was next. So the custom fuel model, the standard fuel model that was the closest to the custom fuel model did the best job of predicting. That's an interesting result right there. And I'll talk a little bit about the impact in a minute. So that's the study. And before I totally wrap up here, I want to give you some caveats, of course, before I do the conclusions. And the first one is the most important, I think. And the point is, in the case of this fire at Hawaii Volcanoes National Park, it's true that a standard fire behavior fuel model was the most accurate in estimating fire behavior. That's not the case in other parts of Hawaii. Guinea grass fuels on Oahu, especially, are very poorly modeled by any standard fuel model. They exhibit fire behavior that's well outside the predicted range. Another important caveat, and this has to do with those RAWS weather stations that I talked about. Those RAWS weather stations produce fuel moistures that are not very accurate for fuel moistures in Hawaii. That was the result of a study done about 8 years ago now. And the main reason for that is the seasonality of Hawaiian fuels is not very well captured. So Hawaiian fuels are weakly seasonal, and what I mean by that is they're there. Those fuels are there 12 months a year. They're there every day. They never get snowed on. They never get trampled down. They're always there. This is in contrast to especially grassy fuels on the mainland, which get crushed in the wintertime, and then in the springtime they sprout and they're super green, and as fall progresses they get drier and drier and drier. That's not how Hawaiian grasses behave. They're very different. And then just a more general caveat, Hawaii has fuel types that just don't exist on the mainland. And it's some good examples of that. Guinea grass, again, this is that 2 to 3 meter high grass they have on Oahu and parts of the Big Island. But also tropical wet forests. They don't really have those on the mainland. And so all of the effort that went into building fire behavior predictions and models and remote automated weather stations for the mainland, a lot of that doesn't necessarily apply to Hawaii. However, there are some good lessons to learn. Those Hawaiian fuel beds that I talked about are very diverse, and that's driven mostly by steep gradients in precipitation and temperature, and those gradients in precipitation and temperature form an extremely complex set of climates. And then the second thing I want to emphasize is that fire modeling in Hawaii has come a long way. It is true that fire behavior models don't work very well in Hawaii most of the time, but as I've shown here, if you do an intensive study, you can make some observations that show, yes, the fire behavior model performs well for Hawaii under certain conditions, but that we have to be very careful about when we apply those fire behavior fuel models and when we apply those fire behavior models. So fire modeling in Hawaii is not quite yet to the level of mainland modeling, and every time we do more fire modeling experiments, we bring up more issues become apparent, and the modeling work moves along and we move forward. I'd like to thank all my collaborators again, and especially like to point out Allie Ainsworth and Rhonda Lowe at the NPS. They were very helpful again with getting this study going. And if there are any questions, again, my name is Andrew Pierce. You can reach me by email or by phone. I'd be happy to speak with you about any questions related to fire behavior in Hawaii, and I look forward to hearing from you. Mahalo.